Hi everyone, I'm Tian. Welcome to the talk on data-dependent locality-sensitive hashing for the Earth-Moon distance. This is a joint work with Rajesh and Eric. Let me start with the definition of the Earth-Moon distance EMD. So EMD is a metric space defined over another ground metric space. And the points in EMD are multisets of the ground metric space of size, say S, and then the distance between 2 points A and B is defined as the value of the minimum cost perfect bipartite matching between elements in A and elements in B, where the cost is measured by the distance function of the ground metric space. And the problem we are looking at for EMD is called the approximate nearest neighbor search, where we fix a metric space X. This is going to be, not surprisingly, the EMD in this talk, and a approximation factor C. And then we are given a data set to pre-process. Later on, a query point in the metric space will arrive, and we are supposed to output any data set point P such that ideally its distance to the query is minimized, but here we allow it to be off by a factor of C. So for example, here the green point is a query and the Y is its true nearest neighbor in the data set. And according to the problem setting, we are allowed to output P as our answer. For the L1 normed space, Indig and Mawani give a very efficient data structure which achieves approximation C and the pre-processing time n to the 1 plus 1 over C, which is subquadratic. That means we do not compute the array distance of our data set. And the query time is n to the 1 over C, which is sublinear, which means we do not scan all the data set points for one single query. So this is good. And we will take this as a benchmark for our AN for EMD. So how did they construct the AN data structure for L1? Well, they introduced this framework of locality-sensitive hashing, LSH. So it's basically a hashing scheme which satisfies the following property for any 2 points in the given metric space. If they are close in the sense that their distance is less than some given parameter R, then the probability that they fall into the same hashing bucket is at least P1. And if they are far, that means their distance is larger than C times R, then the probability they fall into the same bucket is less than P2. So it's really saying close points are more likely to climb than far point. And if we view it as a filtering procedure, it's saying that, okay, when Y is far from X, then we have probability at least 1 minus P2 to filter Y out. Meanwhile, we're gonna keep the close points to X together with probability at least P1. So it turns out that if we have a good LSH, then we are good for the AN problem. And if we define our the quality of our LSH by row, then we can achieve AN data structure with approximation C and the pre-processing time n to the 1 plus row and the query time n to the row. So this is exactly where the 1 over C comes from for the L1 case. Now let me introduce a slightly modified definition of LSH. So the guarantee on that closed points collide remains exactly the same. The only difference here is that we do not require the LSH to filter out all the far from points from the entire metric space. What do I mean? Well, say if we have a far point z from X from the data set, then the data-dependent locality-sensitive hashing is supposed to filter that out with probability at least 1 minus P2. So here, note that Z only comes from the data set. So this allows our algorithm to somehow look at the data set and decide what to do. So hopefully we can get more juice out of it. And this is true when we proceed to later part of this talk. And it turns out that this modified LSH is also enough for ANN, and with a good data-dependent LSH, we can get a ANN data structure with of the same quality as we mentioned before. So now the question becomes, so originally we are interested in the ANN for EMD. Now we reduce that to coming up with a good LSH for EMD. So before diving into any details, I'm gonna give you some intuition on what ANN for EMD looks like. So here is our dataset, which consists of 3 points, A, B, and C, and each point is of size 4. And the query are the stars. So in this example, we are supposed to return the triangles as our answer. Okay, let me quickly define some notations. In this talk, we're gonna fix the ground metric for EMD to be the L1 space, and use N to denote the size of the dataset, and use S to denote the size of each point in EMD, and use D to denote the dimension of the ground metric space. And it's helpful to think N is much larger than S because N is the size of the entire data set, and the S is just the size of a single point in EMD. Okay, cool. So what did people achieve for EMD for AN? Well, it turns out that we can achieve pretty similar guarantee as we did for L1, except that there is an extra factor in the approximation. So in 2004, indeed achieved the extra factor of D times log S, then Andoni indica cross gamma improved that to log squared S. And in our paper, we further improved this factor to order tilde log S, and this tilde notation hides the log S factor. Okay, so why we have this extra approximation factor? Well, if we have to find an excuse, I would say EMD is complicated and computing EMD is already hard. The classic Hungarian algorithm takes S cubed time, and a flow algorithm would take quadratic time. If we assume some well-known hardness conjecture, it turns out that the quadratic time is also the lower bound. So EMD is hard. So how do people understand EMD? It comes to our first subtopic today, the probabilistic tree embeddings. As I just mentioned, the EMD is hard, and all the prior works embed EMD into a simpler metric space. So what kind of simple metric space we should embed EMD into? Well, it turns out EMD over tree matrix is much, much simpler. How simple? Well, greedy algorithm is enough to compute it. What do I? Okay, here is a cartoon that shows how the algorithm works. So we want to match the blue points and the red with the red points in a tree. So what do? We just propagate all of them from bottom up and greedily match them when they meet. So here we match two pairs, then we keep going and keep matching until we match them all. So it turns out that this is optimal. So here is our plan. We want to come up with an embedding from L1 to a tree. Then we can use this embedding to embed EMD over L1 into EMD over a tree. Then we are in the good shape, because from here, we have an isometric embedding into L1. Then we can use Indig-Monwani LSH for L1. So the isometric embedding here basically follows the same spirit of the greedy algorithm I just showed you. I won't dive into the details. To conclude, the game here is really to come up with some probabilistic tree embeddings with small distortion to take care of this part. Okay, now let me introduce two concrete examples of probabilistic tree embeddings, which will be building blocks of our new algorithm. Okay, so those are the probabilistic tree embeddings in prior works on the for EMD. As you can notice here, the distortions of their tree embeddings really correspond to the extra factor in the AN data structure for EMD. Okay, beyond these two, let me introduce one more. In 2022, Chen, JRM, Levy, and Weingarten introduced a data-dependent tree embedding. So how does that work? Well, given a specific dataset, they're going to construct a tree embedding for you with distortion, basically log of the size of the dataset. So this is the first time the data dependence kicks in. Well, in other words, if we use such kind of data-dependent embeddings, then the data dependence will propagate to the LSH for L1. And finally, our final LSH will break the original definition of LSH, but would agree with the data-dependent LSH definition, which is also fine. And by doing that, hopefully we can get more juice here. So next, I want to really focus on the last two tree embeddings and tell you how they work. So here is a meta algorithm for both tree embeddings. So how do they construct the tree embedding? Well, we're gonna remember we are embedding L1 into a tree. So well, first of all, we're gonna recursively subdivide the L1 space to create a tree, and each vertex in the tree corresponds to a cube in L1 space, then we want to map the points to the leaves that contain them. So here is a diagram. We divide the L1 space by the grid, and then we construct the corresponding tree here, and then we put the points in the leaves that contain them. So the final step is to set the edge weights in the tree so that the distances in the tree approximate original distance. So which is represented by the red edge here. Okay, so here is just a cartoon that shows how the tree embedding works. So we're gonna partition the L1 space and divide all the points into say 2 nodes, and then we keep doing that recursively until we reach the leaves, and we put the points in corresponding leaves. Okay, this is a meta algorithm. So the only difference between those tree embeddings is really the way they set the weights. So here in AIK, they set the weights data independently and achieve a distortion of log squared s. And in CJLW, they allow the edge weights in the tree to depend on the dataset points. And the tree also a data-dependent distortion guarantee here. So let's take a closer look at this tree embedding. Okay, what's the pros of that? Well, when our data set is not too large, say it's like poly S, then we can actually achieve a log S distortion here, which is better than log squared. But the cons is also obvious. So the tree embedding is only defined on a specific data set. So in the pre-processing time, we don't see the queries. So the queries might not be well defined. Also, there are in the ground matrix space of the EMD, there are n points in EMD of size S, which means there are n times S many elements in the ground matrix space that leads to a distortion of log n times S, which is bad for us. So we cannot directly apply this tree embedding for our AN task. Okay, finally, I can talk about how we overcame the difficulties. So how about we just try a natural hybrid of the AIK and the CJLW tree embeddings? So consider the following algorithm that construct a tree embedding. We first randomly sample a subset from the original data set of size poly S. Then we're gonna run the meta tree embedding algorithm to split the original L1 space into cubes. Then we get a tree structure. In the last step, we're gonna set the edge weights. So I'm gonna explain how we set the edge weights in this diagram. So imagine x1, x2, x3 are in the random sample omega. So for those orange edges, their CJLW or data dependent weights are well defined, so we can just set them so. So for the blue point, for the blue edge there, since there are no points in the omega, so we can only use the AIK or data independent weights. So what kind of guarantee can this tree mapping achieve? Well, imagine if all the edges we use are data dependent edges, then we know since the size of the subsample is only poly S, we can achieve log poly S, which is log S distortion. But what about a arbitrary EMD point? How is the distortion for those points? We can imagine that as those points get further and further away from the subsample, we're gonna use more and more data independent weights. Then our distortion will go from log S to log squared S. So we really want to do is that we want to say if the EMD points are close to the subsample, then actually our hybrid tree achieves a log S distortion for them. So now I'm going to define what do I mean by being close to the subsample. Well, it turns out that there is a natural definition for that. It's the chamfer distance. So how do we measure the distance between a EMD point to the subsample omega? Well, we just, for each element in A, we're going to find the nearest neighbor in omega. So the blue points are A points, the orange points are omega points. So we're going to find the nearest neighbor in the ground matrix space, and then we just sum them up. And then based on that definition, we can achieve this chamfer extension lemma, which says that what's expected EMD distance between 2 points A and B. Well, this log S factor is what we have to pay, and beyond that, the distortion depends on how close the point, the EMD point, to the subsample omega. So maybe a rough proof idea for that is that consider the optimal matching which matches A and B, and consider the closest point C to A in omega. Okay, to calculate the EMD in the tree, when the A and B start to pay the data independent weights or the weaker guarantee, that's only one, A and C are separated. Otherwise, if C remains with A, then the data dependent weights are always well-defined. We want to pay the data independent weights. So with that lemma, actually we have two cases. So the first case, the data set points are far from, imagine A is a query. So all the, on average, the data set points are far from A. Then we can, in the sense of the chamfer distance. So in this case, we can show that actually AIK LSH is already good for this case. And for the second case, well, we use a lot of data dependent weights. So we know the hybrid tree is good for that case. And we only get the log S extra distortion factor here if the chamfer distance is something poly log S. Okay, then we have the argument that shows that we can figure out which case we are in, and we can pick the right hammer to nail down the problem. So this is the second time we use a very data dependent argument when we're doing the excluding argument. So let me just summarize our path here. We have the data independent tree here and the data dependent tree here. So we can glue them together to get our final data dependent LSH for the EMD. That's it. Thank you.